How do motors precisely adjust space telescope mirrors? Imagine trying to keep a mirror perfectly aligned millions of miles away in space. That's what makes adjusting space telescope mirrors so fascinating and complex. Let's explore how motors and sensors work together to make this happen. Space telescope mirrors, especially those made of many segments like the James Webb Space Telescope or the extremely large telescope, need extremely fine control. They use special motorized devices called actuators that can move the mirror pieces with nanometer precision. These actuators are part of a closed-loop system, meaning they constantly check their position and make adjustments in real time. Each mirror segment is held by several actuators, usually 6 or 7, that control its position in different ways. They can move the mirror along 3 axes, which are left-right, up-down, and forward-backward. They can also rotate the mirror in different directions. Some systems even adjust the curvature of the mirror to keep it perfectly shaped. These actuators have 3 main parts: a drive mechanism, a motion converter, and an output shaft. The drive mechanism is often a small motor or gear system that produces movement. The motion converter, like a screw drive, turns the motor's rotation into a tiny linear movement. The output shaft then transmits this movement to the mirror. To position the mirrors accurately, sensors are used. Capacitive sensors or edge sensors measure how far the mirror has moved compared to a fixed reference point. These sensors give feedback to the control system, which then tells the motors how to adjust. This process happens very fast, allowing the system to correct for changes caused by temperature shifts, vibrations, or mechanical stresses. The goal is to keep the mirror perfectly aligned during observations, often within a fraction of a nanometer. Different types of motors are used for this task. Stepper motors are common because they move in precise steps, making large adjustments easier. For tiny, delicate movements, piezoelectric actuators are used. These expand or contract when voltage is applied, allowing adjustments at the nanometer level. Sometimes, systems combine both types: large screw drives for big moves and piezoelectric or voice coil actuators for fine-tuning. The mechanical design of these actuators is very important. They use flexure mechanisms that allow smooth, backlash-free movements. This helps prevent unwanted jerks or vibrations. The entire system is built to be very stiff and thermally stable, so it doesn't deform or shift unexpectedly. Some actuators switch between coarse and fine adjustments using a tumbler mechanism, which helps save space and reduce complexity. In practice, the James Webb Space Telescope has 18 mirror segments, each with 7 actuators. These actuators can adjust the mirror to within 1/10,000th of the thickness of a human hair. This precision allows the telescope to focus perfectly, even with the challenges of operating in space. So, in essence, motors, sensors, and advanced control systems work together to keep space telescope mirrors precisely aligned. They continuously make tiny adjustments, ensuring the telescope captures clear, sharp images of distant stars and galaxies.